all your nonsense.
Hashtag hey Ethan.
So today we're going to relate velocity, acceleration, and speed to derivatives, which is a really, 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 really important concept. Because look at the why. Derivatives give us the rates at which things change in the world. You want to change the world, you better learn derivatives. I don't think that's the change that it means, but.
Hashtag I'm going to change the world with derivatives.
This is not something new. The instantaneous rate of change of f with respect to x is the derivative of this, right? This was the old way we did derivatives. Remember those lovely limit things? Right? And then we talked about instantaneous rate of change, instantaneous velocity. Maybe we should, well, it says, when we say the rate of change, we mean the instantaneous rate of change. As opposed to, remember from the last test, what does average rate of change mean? Yeah. That's if you have the interval from A to B, then the average rate of change would be f of B minus f of A over B minus A, which really is just slope, right? So when you have an interval, you can do the average, but to do the instantaneous rate of change, we do this limit, which we know now is the derivative, right? So not only does derivative mean rate of change and slope, but we're also going to relate that to velocity here, okay? How fast I can go when your notes are printed out.
Someone almost got killed by a bus. It was so depressing. I was driving to my new house, and this bus was like, big turn, swerving in my lane, and nearly hit me.
Hashtag you almost hit a bus full of school children.
No, the bus almost hit him.
Hashtag murder.
Hashtag bus driver almost hit me.
I don't think he would do much damage to the bus. I think it would hurt him a lot more. Alright, so the beginning of your homework is like this. They're going to give you a problem and they're going to ask you to write the equation and they're going to ask you to find the rate of change. So it says a square of side length S is inscribed in a circle of radius R. What does that mean? A square is inscribed in a circle.
It's like a circle side of a square.
And the corners of the square touch the edge of the circle, right? So let's see how great of a picture I can draw. I'm going to draw my circle first. Here's my circle. And here's my square. And it says a square of side length S, so I'm going to call this S up here, is inscribed in a circle of radius R. It doesn't really matter where you draw that radius in. I'm just going to draw it like this and put an R right there for now. So maybe draw a picture if it helps. But part of your homework is like this, A, B, C, D. You love when there's problems like that, right?
It makes my life so much easier.
Part A says, write the area A of a square as a function of the radius R. That means you need to have A and R in your equation, and that's the only letters that you should have in that equation. So how could we write the area of the square as a function of the radius R? I don't think that's what we should do. Can we just figure out what S is in terms of R? So instead of using S, like what's the area of a square? Let's start with that.
That was pretty
Hashtag this is why I don't play Bible. That's why there's 4.
Later, you're gonna be like,
You're
like blaming your students for taking it.
You're gonna blame calculus.
How do you find the area of a rectangle? Let's start there. But in a square, the length and the width are the same, yes? So side times side, or we could say side squared. But I don't want the area in terms of the side. I want you to write the area in terms of the radius, which means you have to figure out how can you replace S with R, and you can't just replace S with R. But I think maybe, what if I extended this over here like this? Would that be another R? Well, you could, somehow we gotta make a right triangle. We could drop it down and make a right triangle here. I'm going with the big right triangle. What if I made this triangle? We're getting there. That's part B. Part A, you gotta get the equation before you can take the derivative of it. So do you agree that this is a right triangle? This would be S, and this would be S. So could I write the relationship between those three sides using Pythagorean theorem? Yes? No? Maybe? So could I say side squared plus side squared equals what squared? Equals r plus r, which is 2r squared. You have to square the whole thing, right? And do you agree that that would be 2s squared equals 4r squared? So I have to square this whole side over here. S squared plus s squared is 2s squared. And remember, the goal here is to figure out what s is in terms of r. We're almost there. If I divide by 2 here, do I get that s squared equals 2r squared? Which means to find the area of that circle, if you knew, to find the area of that square, if you knew the radius, you could just take the radius squared and multiply by 2, and that would give you the area of the square. So I think the answer that we want to say here, right, the area of the square as a function of the radius, we want to plug 2r squared in for a. So our answer here, I don't really have a lot of room here, is a equals 2r squared. So not all that difficult, but you know, that one kind of is. So instead of giving you the equation, they make you write your own. Now look at part B. It says find the, and they put in parentheses instantaneous, because the book says that when they say rate of change, they're implying instantaneous rate of change. So they put parentheses around there to try to get you ready for at some point, they're just going to say find the rate of change, and you need to know that means instantaneous rate of change of the area A with respect to the radius r of the circle. What does that mean to do? Find the instantaneous rate of change. That's the average rate of change. This is average rate of change. Oh, this whole thing, right? Do we have to do this whole thing to do the instantaneous rate of change anymore? Because that's just the derivative, right? Which means if you want to do the whole limit thing, you can. But all you have to do is use the rules that we've learned now to take the derivative, all right? So instantaneous change means the derivative, which means to do this, all we have to do is take the derivative of this equation. So you could say a prime, right? But I'm going to write it the other way. Take the rate of change, so I'm going to put dA with respect to the radius, dA over dr. That means the derivative of a with respect to r, or a prime, is also acceptable. And instead of doing the limit thing, what would the derivative of 2r squared be? Isn't that much easier than the limit? You were right. I just thought you said, I didn't hear the limit part. I just heard f of a. So I thought you were hashtag guitar hero. I just say hashtag at the end of it. It's cool.
Literally,
You hashtag at the end of the word.
you know, you just leave people hanging when you do that, because they're like expecting something else after that hashtag, and they're like, we will never know what she's thinking.
Evaluate the rate of change of a at r equals 1 and r equals 8. If I'm going to evaluate the rate of change, where am I going to plug 1 and 8 into? Am I going to plug it into my original function, or am I going to plug it into my derivative? Because rate of change means derivative. Alright, so that's not the worst part of writing the equation. Now it's just plugging it in. Evaluate it at r equals 1. So you're just going to plug in 1. And you get an answer of 4. And you're just going to plug in 8. And 4 times 8 is 32. You with me on that? That's not so bad, right? Now look at part D. It says if r is measured in inches and a is measured in square inches, what units would be appropriate for dA over dr? And AP tests tend to ask you to give an answer and put units on it. So it's important to think about for the derivative. And it's really not that bad to do if you just look at the derivative. That's why I wrote it like this instead of a prime. If a is in square inches, you really want, and you want to cancel that out, right? Because you're used to like x squared over x. When we're talking about units, we don't cancel that out. Like we would say that the units here would be square inches per inch, right? So like you can leave your answer like this. You're not going to cancel it out, make it inches, because we're going to talk about how much it's changing. And what we would say is we would say that the rate that the radius changes comparing to the rate that the area changes. So it changes like 4 square inches for every inch of the radius, the area changes that much. So we would say that this changes 4 square inches for every inch of the radius. So that's kind of a weird thing. It's really hard for me because I want to say it's just inches also. But just know, you would leave it like that. So you take the unit of the top over the unit of the bottom. Not always the same unit, so it gets a little better. Like feet per second is how a lot of times it is, because you're talking about like speed over time or something, so, or distance over time. All right, so you have one on your homework like that. I think maybe it's about a cylinder or something. Okay, it is. It's not that exciting, but let's get to the exciting stuff. Here's the exciting stuff. I had all this stuff printed out already. Like I just was gonna move the thing down, but then I decided to print your notes out, so I erased it all so you had it right there. So the position function is something that we dealt with in pre-calculus a lot, and I don't know if we've dealt with it now or not. I think we did. We talked about, maybe not. But it tells how high something is, and normally we think about it like this. We say like S of t equals negative 16 t squared plus b sub 0 t plus s sub 0. Any big memories of that? Where like this is your initial velocity, this is your initial height, this is like acceleration due to gravity or something like that. A lot of times in this book they give you the position function, so you don't have to come up with your own equation. But we did that a lot in pre-calculus. But now we can relate these to the derivative. So if you take the derivative of your position function, the derivative of the height function, that is going to give you the velocity function. So that's something that you need to make sure that you learn, that the derivative of a position function is velocity. So we could say s prime of t, but we could also just label that the velocity function. So if they give you velocity, you have to know, oh, that's the first derivative of the position function. Sounds like it. And then if we take the derivative again, so if we take the second derivative of the position function, that is going to be your acceleration function. And again, I like to think about the different ways we could write this. One way we could write acceleration is we could say the second derivative of the position function, or that would be the same as the first derivative of the velocity function. Do you agree with that? I could write that as v prime of t, the first derivative of velocity. Or we could just write it as the acceleration function. So again, it's one of those things that you just have to be aware that all of those mean the same thing. About the football game? Sure. I don't know. I don't know. I'm hoping to come to the game. How about that? That's my excitement level. The first one I've been to this year. But next week I'm coming to the game for sure because Parker gets to come out at halftime and wear his football jersey. We might only come for halftime. But do you know how speed relates to velocity? Any of you physics people?
Speed is where you end up with the velocity is where your position changes.
Maybe. Velocity can be negative and speed can't. Do you agree with that? Like velocity shows direction, so if something's falling, we can say it has a negative velocity, but speed can't be negative. So the definition of a speed function in terms of what we're thinking is it's the absolute value of the velocity function. So it's still velocity, but it's just the absolute value. So we can say it's the absolute value of the first derivative, or that's the same as saying the absolute value of velocity. So if you know velocity, you also know your speed function. Speed cannot be negative. You can't go negative 55 miles per hour in terms of speed, but you can have a negative 55 miles per hour velocity if you were falling. So now we can do some awesome problems with this. So this is where you really want to pay attention. The homework tonight definitely is not as just straightforward because you got to think through these. So this is why I really printed this stuff out, is for questions like this. And this is actually in your book, number 13. Because it's really, let's figure out this stuff, because this is what you're doing in homework today. Same stuff like this. A rock thrown vertically upward from the surface of the moon at a velocity of 24 meters per second reaches a height of, this is our S function, right? Because we can't use our normal function because the gravity on the moon is not the same as the gravity on Earth. Meters in t seconds. Find the rock's velocity and acceleration as functions of time. So what does that mean to do if we got to find the velocity and acceleration function? Find the derivative, and then find the derivative again. Yes, because velocity is the first derivative, acceleration is the second derivative. So you've got to know that in order to know what to do for part A. So, if this is my function, s of t equals 24t minus 0.8t squared, if I want to find my velocity function, I'm going to take the derivative of t, and I'm just going to write that as b of t. Eventually I don't write s prime of t every time, but I am today because it's our notes. And again, to take derivatives, we don't have to do the limit thing anymore. We can just use our shortcuts, which means this shouldn't be so bad to do. That would just be the derivative of 24t is just 24. That's 1.6, right? Minus 1.6t. And just throwing out there units here, if this is your height, so many meters and so many seconds, when you plug something into your s of t function, your answer is always going to be, in this case, meters, because it's in meters. But if you take the derivative of that, you're now taking the derivative of distance over time. So this would be so many meters per second. And then if we did the acceleration function, that would be the derivative of the velocity function. And what was the derivative of that? Just negative 1.6. And now, if you were doing the units on this, you would have velocity over time. So you'd have meters per second over seconds, right? So that would be the same as meters per second squared. And that's why acceleration is always in meters per second squared or feet per second squared. And again, we'll come back to the unit stuff later, but I just like to show it to you. I guess how loud that is every time that does that. Pretty loud. So look at part B. It says, how long did it take the rock to reach its highest point? So this is where you have to think a little bit. Where would the highest point be if I threw a rock vertically upward? Pretend this is my rock. I won't throw it at you. Right? Where is its highest point? What's that point called? It's going to kind of look like this, right? And so the highest point is going to occur at its maximum. What do we know in terms of calculus about the derivative at a turning point on my graph? The derivative is 0, which means to find the maximum of this, I no longer have to think about putting it in vertex form or figuring out what that maximum is. I can just say, to find when it reaches its highest point, I can just set the derivative, which is the velocity, right, equal to 0. Also think about, do you agree that at that turning point, the velocity is 0? Like it kind of goes up there and it stops for a split second and then it goes back down? Like it has no velocity at that point? So that's another way to think of it. So for part B, I can just set the velocity function equal to 0, because that's when the derivative is 0, that's when the velocity is 0, and I no longer have to do a bunch of other work like we did in pre-calculus to find that. But you have to know what to do on that problem. I extra blank spots to do this in, didn't I? So like, cause we just keep going here, parts A, B, C, D, and E. So if you need to run it to the next one, that's why I have that there. Yes. Questions like this on your homework. So set the velocity equal to 0. So that would be 24 minus 1.6t. That's a minus sign. Equals 0. And then we're just going to solve that, which isn't so bad to do. Negative 1.6t equals negative 24. So divide 24 divided by 1.6. This is in my hand. I got 15. Did you get that? Or do you agree that that's what I would do? And we're talking about time here, so we would say that that would be 15 seconds. Which is just really nice. It's a nice thing to do to solve that problem. What about part C? Part C says, how high did the rock go? If I'm talking about how high did it go, do you agree I'm still talking about the that maximum point right there? Yes? So we need to find where that maximum is. If we're trying to talk about the height of the function, which equation should I be dealing with? The original one, the velocity, the acceleration? The original one. So if we want to find the max height, I better be dealing with that original function. I don't know. What happens? Do I know what value of t that I need to plug into that function to find the highest point? Because if it takes 15 seconds to reach its highest point, could I just plug 15 in there and that should give me its highest point? Like the output? Because you have to think about which equation gives me height, and I can plug it in there. So you really just have to plug 15 there. But again, like the new part of this is you have to think about which equation should I be dealing with? What should I be doing here? And I just did that all in my calculator. I'm just going to tell you, I got an answer of 180. If we're talking about height here, this would be an answer of 180 meters. So we would say that that rock went 180 meters in 15 seconds, which seems awfully high for a rock to go. But it's on the moon. Remember, it's on the moon. That's why, because it's going to float up there for a long time. I forgot we were on the moon. You with me on that part? What about part D? Let's think about this for a minute. But it says, when did the rock reach half of its maximum height? Right, you can't just half the time because it's not necessarily going to be, yes. Half its maximum height. So if we know its maximum height is 180, you agree half its maximum height is 90? So could we just set what equals 90? That height equation. I agree with you. And this is where this one's not so much fun. It was fun up till now. Because this is a quadratic, right? Which means that we have to get that equal to 0. So if I move this over here, because I like to have this positive, that would be 0.8t squared minus 24t plus 90 equals 0. And we could try to get rid of that decimal, like multiply everything by 10 and see if maybe we could factor it, but it's not going to be factorable, which means your options are something in the square or the quadratic formula, and I think I'm a quadratic formula girl on this one. Y'all remember the quadratic formula? You want me to sing the song again? And it's just plugging in your calculator, but it doesn't work out so nice. Like, it's going to be like a decimal answer when we do this. And so you just would plug it in, and we would say 24 plus or minus the square root. I'm just going to put 24 squared. Some people always say, why didn't you put negative 24? Because it's always going to be a positive, and don't make a mistake with your negative, so I don't ever put the negative there. Minus 4 times 0.8 times 90, all over 2 times 0.8. And my suggestion is type everything under that radical in your calculator at once so you don't make a mistake. And so when I did that, I got 288 over 1.6. And this is where we're talking about time here. So I know I'm not a big decimal fan, but when we're talking about a story problem, we're talking about how long does it take to get there, a decimal makes way more sense than leaving your answer like this. And so you just would want to work it out and get your answer or answers, I guess. And so I just do the top first. 24 plus radical 288, hit enter, and then divide by 1.6. You do it all at once, you have to put the top in parentheses, right? So if you want to type that in all at once, you better put that in parentheses. But I just always do it a step at a time. Like 24 plus the square root of 188 divided by, goodness gracious, it is 288. Let me just, I don't know the answer already, so I'm not even going to type it in. Look, I wrote X there, but it's really T. I don't know which one you get. Rounded 3 decimals because that's what you have to round to on the AP test, so it's just good practice. So, Sean, what did you get at 3 decimals? 607. And then if you go the other way and you subtract 24 minus the square root of 288, and you divide that by 1.6, you get 4.393. And just so you know, the AP test doesn't care if you round or truncate that third decimal, which means if you just go to 3 decimals and you stop and you don't care what's after it, they count that. Like on the AP test, if, I don't know what was after this number, but let's say there was an 8 after this number, if you just put this as your answer, they would count it right. Or if you rounded that up to 608, they would count that right as well. They just want 3 decimals. Isn't that kind of weird? It's like it goes against everything we've ever done with rounding. But like you already rounded up, right? Yeah, I'm just trying to explain that. So here's my question. Are both of these the answer of when the rock reached half its maximum height? It definitely reaches that twice because it goes up and it comes back down, right? Like, so it's going to reach 90 here, and it's going to reach 90 over here as well. Yeah, I guess maybe. I just circled the smaller one because I said that's like when it came up, but I don't know. I could be convinced to give both answers. Right? Right, like it's always going to do it twice, but I just took it to mean, if you ever got a negative answer, obviously you couldn't have negative time, so that's not a good answer. Oh yeah, we could put units on there, seconds. Almost done with this one. How about part E? The thing is, doing this should help you on your homework today, because you're going to see the same types of questions. So if you get stuck on what to do, I'm hoping that you'll be able to go back and look at this. I'm going to come over here for part E. How long was the rock aloft? Hashtag you complain a lot.
I'm not complaining, I'm making a statement. There's a difference.
Anybody got any ideas on this? I'm not trying to think of a good question to get you to get to the answer without just telling me. If we think about using the first equation, the height equation, what's the height when the rock reaches the ground? 0. That's also when it starts, right? But I think to find how long was it aloft, instead of setting it equal to half of its maximum height or whatever, I think we could just set the height equal to 0. Just be aware, it's also going to tell you it's at 0 seconds it was at 0 because it starts from the ground. But the other answer that you get should give you the maximum height of that. on this one, do you have to do the quadratic formula? So you could, but you don't have to. I would just factor t out of that. I'm sure you could factor something else out, but I just factor the t out. So you get t equals 0. That's when it starts, so that's not the answer. And then on this one, you're going to get t equals negative 24 divided by negative 0.8. And I think I got 30 seconds. Is that right? Which does kind of make sense, I think. What did we get at B? How long did it take the rock to reach its highest point? It took 15 seconds. If our path makes a parabola, does it make sense that how long it takes to reach half, it's going to be symmetric on the way back down, and it does make sense to just double that? Yeah, so maybe if you knew that, you didn't have to do that. All right, so that one kind of took a lot. The next one I feel like doesn't take as long. It's, again, just kind of reading what it's asking and knowing what to do on this. I don't know. I'm going to hold you hostage.
I have English.
Come on, you know you'd rather stay here than go to
You're right, I would.
Again, a particle moves along a line, so its position anytime greater than or equal to 0 is given by this function. So again, they're giving you the position function where s is in meters and t is in seconds. Find the instantaneous velocity at any time t. What does that mean to do? Find the derivative. Velocity means derivative. So for part A, all you're doing is finding the derivative in terms of t. So I'm going to say s prime of t equals the velocity function. And again, this is just the power rules here. So we're going to bring that down. So degree, that's negative 3t squared plus 14t minus 14. Part B, find the acceleration. What does that mean to do? Take the derivative of velocity. So we can say that the derivative of velocity is the acceleration function. And that would be, what? Negative 6t plus 14. Part C says, when is the particle at rest? What does that mean? When it stops moving. So what is the velocity of your particle if it stops moving? 0. So maybe next to this, right, that means when the velocity equals 0. And that's the big thing that we're practicing on our homework today. Do we know what that question's asking? The solving it part is just kind of annoying because this one is also quadratic, which means I really don't want to waste the time of doing it for you because I feel like we can do the quadratic formula. But we would solve this. Negative 3t squared plus 14t minus 14 equals 0. And then let's just write underneath that quadratic formula. And are you okay if I just tell you the answers to that? It works out to be at 1.451 seconds and at 3.215 seconds. Now look at part D, and on your homework today, on the odd problems that say describe the motion, I want you to look in the back of the book, because they put it a lot better than I do. When it says describe the motion of the particle, what they mean is you should be able to tell me whether the positive is moving forward or backwards up until each change, and then at these points it changes direction, because if it stops moving, it's going to change from going forward to going backwards, or from going up to going down. And so how do you know? Plug in a number smaller than 1.4, or think about plugging in 0. So think about, like, if we plugged in for part D, did I get to leave you 2 pages on this one? If I plugged in 0 to that original function, where would my particle start? This one, not the velocity. If I plugged in 0, I would get 8. Do you agree with that? So I could say at time t equals 0, the particle is at 8, or it starts at 8. And it keeps going until it stops at 1.451 seconds. So I could say is at 8 and goes until time equals 1.451. Yeah, and we really could say, like, is it going positive or negative by plugging in another number. Let me do that really quick. If I plugged in 1 into this, negative 1 plus 7 minus 14 plus 8. If I plug in 1, I get 0. So if I plug in 1 for time and I get a smaller number to 8, does that mean my graph is moving like in a positive direction or a negative direction? Negative. So I could say, and it goes in a negative direction. Let's put that, and goes caret. You ever use that in your editing? Does Ms. Dobson ever do that? Caret. And until 1.451. Then, after it goes in, this stopping point means it turns, so I don't have to plug any more numbers in. If it turns at 1.451, which way is it going now? Then it goes in a positive direction until when? Until the next stopping point at 3.215 seconds, when it turns back to a negative direction. And I just want you to make sure, like, I'm fine with you looking in the back of the book on these, but you can tell me about that function without ever graphing it, because we can think about slope as being positive or slope as being negative. Okay, and so we're going to skip the last one for now, which means there might be 1 or 2 on your homework like the last one that I'm fine with. Day 2 of this is a lot easier than day 1, and I can tell you day 2 homework I think is only 4 problems as compared to today's homework, which is a lot of problems. I'm trying to tell you, try these. On Monday, your homework is only 4 problems. So if you don't get these all done this weekend, right, I hope you do some of them, but if you don't get them all done, Monday's homework is only 4 problems, a lot easier, and so then Monday night you can go back and pick up the ones that you didn't do on here. Does that make sense? Because today's homework is a lot harder and a lot more than Monday's homework. And Monday's is going to be a lot easier, and you're going to be like, oh my gosh, why wasn't day 1 like this? So I'm trying to tell you. Oh, thanks.
And so are we allowed to graph it to see, or do you want us to figure it out before?
On the test, I can tell you there's a question that you're not allowed to use graph calculator on that I ask you to describe the motion. So my advice would be try it before, but then if you want to graph it, you can verify that you did it right. Like definitely your graph calculator is a tool to help you, but try to do it without looking